Same paper 9701, paper 41, May June 2023. Question 2, part A. Some transition element complexes can show stereoisomerism. State two types of stereoisomerism shown by transition element complexes. तो अगर आपको याद हो, in transition metal complexes we used to discuss two geometries. The first one was geometrical and another one was optical isomerism. So optical में we used to see mirror images, and in geometrical isomers we used to draw cis and trans. Trans means opposite at 180 degrees, and cis बोले तो 90 degrees, like they are on the same side. Okay, so that's why I have written like the two geometries that are possible, like the two isomers, geometrical isomers and optical isomer. In part B, they are saying the complex is platinum, then ammonia, then chlorine. There are two different ligands. It's the case Ml2X2. I told you in with different cases. Sometimes we have three same ligands, one different. Sometimes two different. Sometimes we have. So it depends on the nature of the transition metal complex. So in this question, they have given you the two different complexes have the same geometry, so shape around the metal ion. So they are saying this compound exists as two stereoisomers, whereas this, like platinum En2, 2 plus only has one possible structure. You know, they have the two En ligand, like the two same, and En is bidentate ligand. En is bidentate ligand. So I can say there are four ligands, four same ligands. Okay. So state the geometry around the metal ion. State the geometry around the metal ion. Okay. So this compound would not give you stereoisomer. Like I'm talking about platinum En2. Why? So, for stereoisomer, the mirror images should not superimpose on each other. So they are the same ligands, so they would superimpose on each other. So I cannot say that they are going to give you stereoisomer. If you can talk about this, so there is a confusion between, like, whenever we see the coordination number that is equal to 4, so the 4 is quite confusing number, whether the compound is going to give you tetrahedral, whether the compound is going to give you square planar. So remember, whenever you can see this situation, that is Ml4, so the geometry would be tetrahedral. And whenever you can see this situation in which the two different ligands and same ligands, like ammonia same, chlorine same, but overall they are different. So 2:2, right? So in this situation, the complex is going to give you the square planar geometry until or unless the coordination number is the same for both, for tetrahedral, for square planar. That's why I'm saying until or unless the coordination number is same, but in this manner, you can you can predict whether, like, the geometry is tetra, and you can say square planar. Okay, that's it. And and the complex CrEn32 plus. Okay, so in this complex the coordination number is 6. Why? Each En is going to make two bonds. Each En is going to make two bonds. So obviously you have 3 En. Ultimately they would be forming 6 bonds. That's why I'm saying its coordination number is 6 and the geometry would be octahedral. Exists as two stereoisomers, whereas the complex this exists as 4 stereoisomers. Complete the 3D diagram in figure 2.1 to show the 4 stereoisomers of this complex. Represents the ligand this by using O and N. These corners are going to show the carbon atoms, CH2 and CH2. Okay, so they have given the 4 different spaces, and then I have to fill it. Okay, and we have to write down the different isomers, right? Okay. So first of all, I would be drawing you can say I have this complex, right? I have this complex, and this ligand can be represented by this manner. Okay. So we have three ligands, and it's gonna give us the stereoisomer, or I can say optical isomer. So I have drawn the mirror image. When you are going to draw the mirror images, so your left becomes right and your right becomes left. You can match it. They are exactly, they are opposite to each other. They are mirror images of each other. They are mirror images of each other, so they are not superimposed on each other. That's the reason I can say they are optical isomers. And if you talk about this isomer, that is EN3, or the same thing basically, okay, the same thing, like ethylene diamine, which is bidentate ligand. So, then what can I do for this? What can I do for this? What they are asking? They are saying exist as four, exist as four stereoisomers. Four stereoisomers. You know what can I do? I can do cis trans. I can do. Wait for 1 minute, Azan. Okay, so I have to draw more two isomers. So you can see okay, oxygen and oxygen, then oxygen, then oxygen. Okay, so this is different pattern, and I can also draw another two isomers in which the pattern would be different. Like I mean to say, I should attach the opposite side. You can say I'm going to change the side just like that. I'm going to change the side, and then this would remain the same, but I'm twisting this, or the same goes over there. Okay, and then again I'm going to write down the going to connect the different ligands just like that. Okay, in this manner, or you can see this, right? You can see this. So in fact they are also the mirror images. Okay, or if you can compare this with this, okay, if you can compare, so you got an idea. Okay, like what is the difference between them? So they are four stereoisomers. They are four stereoisomers. Since this is octahedral shape, okay, so obviously in the question they have told us that they are going to show the four stereoisomers. So you have different options to draw different structures. So that's the reason I have drawn like these structures. And in part D, they are saying the complex is formed by reacting chromium 2 plus with the conjugate base of 2 amino ethanol. A synthesis of 2 amino ethanol is shown in figure 2.2. Suggest the mechanism for step 1 for of the reaction of oxirane with ammonia in figure 2.3, or include all relevant curly arrows, lone pairs of electrons, charges, and partial charges. They are, they are saying charges. What does it mean? Charges and partial charges. Partial charges means just like that, partial positive and partial negative, and only charges means the full positive and full negative. Generally, this charge is on polar covalent or like strongly polar, or also in ionic compounds. To draw the structure of the intermediate, draw the structure of the intermediate. So, it's going to react with this ammonia, in which you can see one lone pair of electron on the nitrogen atom. Since this carbon is having a partial positive charge and this oxygen is having a partial negative charge, due to the presence of highly electronegative element, due to the presence of highly electronegative elements, it's gonna, like you can say, it's going to attract electron pairs. As a result, it would be coming partial negative, and which is making this carbon partial positive. So as a result, this nucleophile is going to attack on this center, which is positive. Ultimately, the bond between carbon and oxygen is going to break down since the electronegativity is higher. It's more polar, or I can say the valency of carbon cannot be more than 4. The valency of carbon cannot be more than 4. So that's the reason this bond is going to break down. Or what would be the structure? What would be the structure for the intermediate? What would be the structure for like intermediate? So I can say, okay, um, you have, like you can say, this bond is being broken down. Okay, this bond is being broken down. It would be just like this, O negative, and this oxygen is connected with the two carbon atoms. This is the first carbon atom, this is the first carbon atom I have, this is another carbon atom I have, and this carbon is connected with NH, this carbon is connected with NH3 plus. Since the nitrogen has made 4 bonds, so that's the reason nitrogen is having positive charge and this oxygen is having negative charge. So this is your intermediate, and finally it would be reacting with H. Okay, so it would be forming this compound. So they have given you the final compound, so just we have to draw the structure of intermediate. This is of 3 marks. A small amount of byproduct E shown in figure 2.4 is produced during the reaction. Shown in figure 2.2 suggests how the formation of byproduct E can be can be minimized. You can see that you have two OH groups. You have two OH groups. So you can say that NH2 is not present over there. NH2 is not present over there. Only you can see OH. Only you can see OH. Okay. So as they are saying that this is the byproduct, that is E, can be minimized. So what is the difference between this and this structure? So how many carbon atoms it has? One, two, then three, then four, then three, then four, in which you can see only two carbon atoms. Okay, so a small amount of byproduct E shown in figure 2.4, this is figure 2.4, is produced during the reaction shown in figure 2.2. Like they are talking about this reaction. It's the byproduct. They are saying it's the byproduct. So how can I minimize this product. I don't want to have this product. I don't want to have this product. So I can say that limit, I can say limit the amount of oxirane, you know, it's oxirane, which is carbon containing species. This oxirane has been broken down to give you this product, right? So if you have limiting oxirane, so how can I expect that it would be producing this product? Ultimately, when you have more oxirane, so you will be getting this product. And if you have less amount of oxirane, okay, so you won't be getting this product. That's why. Okay, that's why it's of 1 mark only. Compound F, that is C4H9O. I don't know what is this. C4H9NO can be formed from the reaction of byproduct E. Byproduct E with concentrated H2SO4. Compound F is a saturated and basic organic compound. Saturated means it would be having a single covalent bond. Suggest a structure for compound F. State the type of reaction undergone by E to form F. So first of all, I want to know that what is E? E is this. E is this. I'm going to add concentrated sulfuric acid in this. You know that this is a dehydrating agent. This is dehydrating agent. It removes water. It removes water. It removes water basically. When when it would be removing water, this OH and this H would be removed, minus H2O, they are going to connect with each other. They are going to connect with each other. So there would be a bond with this carbon. This is 1, this is 2, this is 3, this is 4. So the one side is connected with this oxygen, basically, right? With this oxygen. So how can I draw this? How can I draw this? This is 1, this is 2, this is 1, this is 2. So uh, the first position, the first position is connected with the first position is connected with oxygen. The first position is connected with that oxygen. Okay, I mean to say the first carbon is connected with this oxygen. It would be making a ring. It would be making a ring. Okay, so so and I can say here are two remaining carbon atoms. Here are two remaining carbon atoms, or then we have NH bond. That's it. This is the structure for compound F. It has a single covalent bond. It has a single covalent bond, or it's basic. Why? Because it contains nitrogen and it has a one lone pair of electron. It can give its lone pair of electrons. So that's why this is the definition of base. Base is going to give us, base is an electron pair donor. That's it. So what is the type of reaction? It's dehydration. When water is removed, so as a result, this product is formed. That's it. Okay. Uh, so this is question number